Okay, so we're solving for b, and this is a what kind of equation? So how should we look to solve it? Like, what's our first effort? Actually, before I ask you that, let's say with a bx term. Which term is the bx term? Negative 13b. So what's our method of choice when we have a bx term? At least to start. Star. Well, that's part of the process, but factoring is the method, right? And yes, we need to set it equal to 0 first, so add 3. Good. All right, and then star, hopefully you checked for a GCF. Is there one? Don't forget to check, because it makes it harder if you don't pull out your GCF, makes it harder to factor, but also your factors will be wrong if you don't GCF. Not the answers, but we don't always care about the zeros. We sometimes just want to factor. This is positive, so 36 is A times C here at the top. What goes at the bottom? Negative 13, so B. A is 6, and it goes on the sides. So we're looking for numbers that multiply, what we call factors, so numbers that multiply to make 36 and add 2, negative 13. Okay, what are those? Yeah. Negative 9 and negative 4. Okay, next step is to reduce. So then reduce if possible. Can we? Yep. So this one becomes 3 and negative 2. So in other words, divide both by 2. And then over here, divide both by 3. And we'll get 2 and negative 3. So our factors are 2x minus 3, 3x minus 2. Okay, now what? That's factored, but we want solutions, zeros, roots, x-intercepts. That's what we're looking for. Yeah, so since something is multiplied and making 0, let's check where that happens. So 2x equals 3 and x equals 3 halves. Over here we do the same thing. 3x equals 2, x equals 2 thirds. Now it is just, it's not like a pattern or anything that they are reciprocals of each other. It's kind of interesting in this case that it is, but don't make that into something. So where'd you get confused? Those of you who said you got lost. Where? Zeke, where?
When I was figuring out what adds to negative 13 and 36, I got confused. I forgot.
The two purple factors, negative 9, negative 4. Same. Where'd you get stuck, Saphira? Where? Okay. So here's my advice, those of you getting stuck on that. Start at 1. So just make a factor list. Start at 1. 1 times 36. Can I make 13 out of those two numbers? No. And then 2 times 18. Can I make 13? No. 3 and 12. Can I make 13? No, but I'm getting closer, right? Now we can make 15 out of that. 4 and 9. Oh, yeah, that works. And then you just mess with the sign, right? But make your factor list if you're stuck. Definitely don't just sit there.
Doesn't the biggest number have to match like the B term sign?
Yeah, yep. So the bigger of your two factors, the bigger number matches the sign of B. That's something to keep in mind. In this case, they were both the same, but. All right, raise your hand if you got both factors correct. So 3/2, 2/3. Let's kind of check in on that. 1, 2, 3, 4, 5, 6. Okay. All right, well, I should have your test back to you Wednesday. So I usually grade in order that students do them. And so the other geometry class took their test before you. I'm about done with theirs, and then yours is next. So we'll talk about that on Wednesday. So new unit. If you have my notes, let's go ahead and start the title at least. And then if you have your own, I would create a new section. And this is unit 7, all about similarity. Geometry is so interesting because we have such different unit names and titles and concepts than the other maths that we do. Like we would never, well, maybe not never, but just as similar, the word similar is a title of a unit. It's cool. Geometry is good stuff. What does similar mean just in everyday language? Closely alike. Could we say it like that? You guys agree with her? Okay. Does it mean the same? No. So we just finished 2 units ago. We finished congruence of triangles. That was the name of the unit, triangle congruence. This is not that. This is not, are they exactly the same? It's, are they similar enough that we can mathematically consider them similar? And a big concept in this unit is actually something you've been doing since probably 7th grade. So subtitle this proportionality. Now, for some people that doesn't help, but you've actually been doing proportional relationships or proportional reasoning for several years. And it's something that you do a lot in just everyday life, in fact. How many of you have ever followed a recipe before for anything? Even if it's like how to mix chocolate milk with powder or Kool-Aid or whatever, right? Okay? So most of you are raising your hands. That's, if you scale that recipe to make a bigger batch or smaller batch or amount, that is proportional reasoning. So if I say you need 2 cups of sugar for this recipe, but you're making 3 times the recipe, how many cups do you need now? 6. You just did a proportion, okay? So we're taking that concept and expanding it a little bit to figures, to how can we use this in general, but also specifically in similar triangles. And we can end up doing some pretty neat stuff that allows us to solve for things that we couldn't solve for otherwise. So at some point in this unit, we'll be able to go outside and use this concept. And it sounds a little bit hokey, but we'll be able to go outside and use shadows to find heights of things like light poles or trees. We'll be able to use their shadow to do that. We'll be able to set a mirror on the ground and figure out how tall a tree is using a mirror on the ground. It's cool. It's kind of like magic, but it's obviously just math. All because of proportional relationships, and it's pretty neat stuff. So let's kind of get into what we mean by proportion and proportional, and how do we solve those, etc. So anybody want to volunteer a description of what proportional or proportion means? Anybody know or have a guess? Were you going to give one?
Wait, what did you say?
Like, what does proportion or proportional mean to you? Do you have an idea?
It just means like
And you kind of have a hint right here a little bit.
I got no reason to just kind of like explain
Okay, well, let's think through this then. Because you guys, like I said, you just did a proportion, excuse me, when I asked you about the recipe. So let's say whatever ingredient we're talking about, let's say it's 1 cup. I don't know why I put an S. 1 cup to 2, let's say we're making bread. 2 loaves. How many cups to 4 loaves? And so you just told me a second ago, oh, well, if we doubled how many loaves we're making, we're doubling that ingredient, right? And so you could say, oh, it's 2. Well, that's proportional. And if we boil this down, we're showing that they are equivalent in value, even though they don't look to be maybe on the surface. Okay? Does that make sense? These ones, hopefully to your eyes, 1/2 and 2/4, you pick up pretty quickly that they're equivalent, but that's not always the case. Like, you can't always just eyeball it and say they're equivalent. Okay? For example, if we had something like this. Well, we don't know what x is, but we could solve for it in a way that makes these equivalent. Do you agree? Okay? So that's the idea of what we're doing here, like understanding what that equals symbol is telling us and how we can use that fact to solve for variables that we have set up in a proportion like this. Okay? So this blue thing, this structure, same with this pink one, those structures are called a proportion. It's saying that 2 ratios are equivalent in value. Or fractions, you can call them that too. But they're equivalent. Okay, so I shouldn't see things like stuck over here like +7. That is no longer a proportion. Okay? It's 2 fractions or 2 ratios that are equivalent.
What if it's x plus 2 over 7 plus 7 equals 3x minus 5 over 14 plus 7?
Well, then we can just cancel the 7s and we're back to this. Yeah. But the initial statement is not a proportion.
But could it be like, could that be a thing like where it would be plus another number, but it would be like in the same like ratio, like the same proportion?
Well, not by definition of what a proportion is. It doesn't mean they're not equivalent. It just isn't a proportion. Yeah. Yeah, good thinking though. Okay, so here's some easy ones. Actually, let's go write that and then we'll come back to that concept. This is going to be a guiding principle of this entire unit, in fact. So it's pretty critical to understand. I'm putting or fractions in parentheses because I think our brains go to, if I show you something like x over 5, your brain is saying, oh, that's a fraction, more so than a ratio. Here's a typical way of showing that. We'll use like A, B, C, and D. To represent, maybe it's just numbers, maybe it's entire expressions, but we're just saying that these 2 ratios, A to B, is equivalent in value to C to D. Do you guys remember learning this in 7th grade? Maybe for you guys it was 6th grade, if anybody was in accelerated math then. Does it seem familiar? Like, so far this is like 7th grade math review. Does it feel that way? Okay. If not, I mean, you're getting it now, so that's okay. All right, and then similarly, let's just define proportional. That's an adjective, right? It's kind of weird to write it twice. I'm going to show you why we are in a second. Two ratios are equal or equivalent. Now, we have some easy, kind of quick, easy ways to check this, and I'm going to put those on here. But now I want you to try a couple of these before I do. So now we know what proportional means. Here's that question again. Write whether each pair of ratios forms a proportion. So here's what I was saying a second ago. You can't just look at some of these and be like, oh yeah, those are proportional. I mean, you can do a little work in your head, like a little... Some of them, it's obvious they're not, but the ones that are close, it's not necessarily immediately obvious. So let's look at the first one. Do you see how the top number in both is bigger? So that starts us off by saying, well, it could be. Versus this one, what do you notice right away in that one?
The denominator, one denominator's bigger and one denominator. Right.
Is there any way these two are going to be proportional in number 2? No way, because this one is less than 1 and that one is greater than 1. And we just wrote that proportional means same value. So there's no way that those two will be. So we didn't really need a strategy for that other than having a brain. But this one, that one's not so obvious. 12/7 versus 36/20 over 21. Like this one, both numerators are bigger, both could roughly be in a similar relationship. So how do we check? Give me a strategy that you could try.
Multiply one side. Like multiply 7 by 3, multiply 12 by 3.
Okay, here's what he wants to do. He wants to basically make our ratios or our fractions the same denominator. So times 3 over 3, and now we get 36 over 21. Oh, well, that's obviously now a proportion, right? They will sometimes, let's say it this way, sometimes you won't see that, what we call scale factor. That's going to be a big word in this unit. This is the scale factor, but sometimes you won't see that and be able to use it to determine if two are proportional. But that's a good strategy. That's absolutely a good strategy.
Can't you just divide 4 by 7 and divide 36 by 21?
You could also do that. Method 2, maybe. 12 divided by 7. 36 divided by 21. After all, that fraction bar means division. So grab your calculators and tell me what that equals.
1.71.
Okay, here's what he said, 1.714, right? Okay, so is it a proportion? Do they have equivalent value? Yeah. Yes, they do. Okay, there's actually another strategy that we could try. Anybody know what it is? Yeah. Okay, so you could divide left and right, he's saying. The thing about that, well, what did you get? Did you do it? Well, try it. Yeah. Now, the thing I was going to say, so let me just show you. If we have this, instead of the and there, if we have it as an equals sign. So instead of and, I just changed it to equals. your first thought isn't necessarily to divide this way, but it's okay to do that. So keep that in mind. Or we could have gone this way. 36 divided by 12, 21 divided by 7. That's also okay. Yeah.
So we're going to multiply both sides by 21.
Okay. So he wants to do, I think this is what you mean. Just multiply by 21. This becomes 3, and we'll get 36 equals 36. Okay? Good job, guys. I'm impressed at all your different thoughts on that. All right. Let's try, let me get that so you can see it's a 7. And organized okay for you. Let's try this one. Number 3. Let's just think in your head, is it a proportion or not? And then I'll just have you say yes or no. Yes or no. Okay, go ahead and vote. That one's no. One reason that you can tell? Well, what's the most obvious reason?
The denominator.
This is more than 1. Let's just write it in math. So this is greater than 1. And this one is definitely not greater than 1. Can those be proportional? Okay. How about number 4? Okay, so I'm guessing since a lot of you said yes right away, did you think of it this way? Okay, so that's similar to this method where we just said multiply by 3 over 3. If we can multiply both things by the same number, which we call the scale factor, and it is equivalent, then it's proportional. Okay, so how about number 5? So maybe try a different method this time. Okay, I'm seeing yeses and nos this time. Kenzie, what method did you try? But what did you do with the calculator?
10 divided by 24.
And what does it equal? Huh?
26.
Oh, so you didn't do a decimal. Okay, well, we could also just say equals 0.4 for those of you who don't have the calculator that does that. Okay, so they divided. Anybody else do it differently? Corbin?
I just did 10 times 2.5 and 24 times 2.5.
Okay, so he did the scale factor method. Times 2.5 times 2.5. And so that's another method. You could reduce both fractions to the same thing.
I saw that like 10, 25. Both are they could both multiply to make 100. So I did 24 times 10 and 10 times 10, which would be 100 over 2, 140, and then 25 times 4 and 60 times 4, which would be 100 over 24.
Okay, I understand what you're saying. I'm trying to think if that's a valid strategy. Here's what she said. No, you said, what did you say on the bottom? Also by 10? What do you guys think? In terms of our definition, we are multiplying two different fractions by two different things. The fact that we can get them to the same value, I don't think that's a safe way to do this. Here's why, because let's say take something that's definitely not proportional and see if we can do that as well. Because I need to rethink through. I need to think through this more. I like that you're coming up with new ways. Let's say we wanted the denominator to be something. Let's say 40. Not times 40, sorry. Times 8 over 8. Okay, so I think it does work because we're multiplying both by 1. Yeah, so it is. It's an okay way to do it. I'm not going to say it's the best way, but it does work. So good thought. Good job. Here's what I just told her, and just to clarify. Both of these are multiplying by the equivalent value of 1, right? 4 over 4, 10 over 10. So I'm not changing the value of the ratio, just changing the numbers. Okay, cool, good job. That's awesome. Okay. Are there any other ones here? Let's do that one. That one's kind of weird. One reason I wouldn't recommend that is because it's hard to think of ways to make the fractions be the same. Like, think about this one. What are you going to multiply 6 and 48 by to make the denominators the same? You know what I mean? It would be a little bit of a pain. Not that it's not a good strategy, just probably harder to think through versus just dividing them, right?
8 by 8.
Good. So maybe it wasn't that hard. Okay, yes or no?
But yeah.
Okay, I'm seeing a no and a yes so far. Okay, well, here's a couple things. A couple of ways, I mean. This is times 8. Is this times 8? Because if it was, it would be what on the numerator? It would be 56. Okay, another thing we could do is reduce 13 goes into 52, but not 48. So let's do 2 and then... Okay, that's as far as we can go. 13/12 isn't a multiple of 7/6. Did anybody do the decimal version? I'm guessing calculator girl back there did. 1.17 or so. But isn't it 6 repeating? Yeah. So I'm rounding. Okay, what's this one? 1.08. Okay, so we're probably confident that it's not. How close can the decimals be to say, yes, this is proportional? Like, not this problem, but if we just think of, like, what if we got 1.17 and we got 1.15? Would you say it is or is not? What if it was 1.1782 and 1.1780? Is that proportional?
No.
He says no, pretty confidently. Do you guys agree?
Yeah.
Okay, let's throw this in the mix. If you're making a cake or making juice, whatever, does it matter if you're off in the 10,000th place?
No, but it's not. It's math. It's different.
Would your juice taste different if it was off in the 10,000th place by 2 10,000ths?
No, but it's different because it's math. You can't say something's congruent if it's just not. It's not the same.
Unfortunately, you're wrong.
But
Because context is an extremely important driver of result.
yeah, so in the context
90% of things in life, or maybe even more, wouldn't matter in the 10,000th place. Money doesn't matter in the 10,000th place, right? If I told you this was price of an item, what would you say? If we're buying a few, who cares? If we're buying 100 million of them, then yeah, it probably would then, right? Do you see how we can't just say hard and fast yes or no when it's like this? Okay, let's do some more. If I'm building a house, if I'm off, if my proportionality quote is off by 2/10,000ths, is the house going to work? Could you even see 2/10,000ths of an inch? No? So houses can be up to like a quarter of an inch, like the width of this pencil is still acceptable to be off that much. So this would be completely fine. If we're building a cylinder for a jet engine, how about then? Would you want it to be off by 2/10,000ths? Probably not, right? That kind of tolerance is way higher now. If you're doing surgery with a laser inside of somebody's body, 2/10,000ths might be the difference between a good outcome and a bad outcome, potentially, right? That would be robotic surgery, certainly
that's
not
what I'm
human
saying.
surgery.
I'm not wrong because it just depends on the context.
You're wrong to say that mathematically it's not proportional, because mathematically it depends. How many significant figures do we care about? Have you heard that word before?
Yeah.
So if we're significant out to the 10,000ths, then no, it's off at that point. But if we're significant out only here, then it's just fine. So we don't want to just say absolutely yes or no until we consider the context. So if you're just strictly saying, well, Mr. Eckerson, if there's no context, are those proportional? Then I would say no, they're not. Do you agree?
Yeah.
Okay, good. This is interesting stuff to think of, right? Saphira, what? You don't care? Okay. It's those of you going further in math, unfortunately, we expose students mostly to the mundane. And it's not until you keep going that you're like, wow, this stuff is freaking cool. Like math can do amazing things. But you don't ever get there if you just do high school. Like it's just like, more of this. Well, what if we have an N or an X or something in there and it says solve? Now what? Now you can't say, well, they both equal and then solve, right? And just to give you a heads up, like what if we add some stuff? Like we have b minus 1 in there and we can't just guess. What if this is b squared minus 1? And there's no way we can just glance at it and be like, oh yeah, that's what it is. We need a strategy, right? You guys call it a strat. I've heard that before. So let's go put that in here. We'll come back and do a few. If we boil down the best methods from what you guys just did, here's probably my 2 that I would recommend. To determine, I didn't even tell you this one, but this is how we're going to solve, so I want you to use this one. I'll go back and show you what I mean, but are the cross products equal? What is a cross product? Okay, so be careful, that means diagonal. This isn't always the best way to answer if it's proportional, but it is 100% the best way to solve. So let's put a couple more methods in here, but are the quotients equal? The quotients being that we divide top by bottom. Now, we haven't defined scale factor yet, but that's what you guys were doing when you said, can I multiply this by 3 and get on both top and bottom and get the same thing, etc. Okay. That I want you to do these. With some flexibility, but certainly when the proportions get weird, you really want to just use the one method. In this unit, we switch the word proportional to similar once we start talking about figure relations. Let me know when I can go to that section. All good there? So it's good just to have a consistent approach. That's what this example is for. Okay. Certainly, I can't look at this and tell you what x is, can you? That'd be cool if you just guessed it right now. So, we're going to use the one that I wrote first in the list, which is to set the cross products equal. Do you guys want to break and come back to this? Okay, let's do that.
I used to have one like that when I was in computers. They freaking broke it. Yeah. Yeah, I how'd you remember that?
Sometimes people think this kind of looks like a butterfly. You can make it look like one. I'll show you what I mean. In terms of, so we're just going to set those equal and then we have an equation to solve. It's actually pretty nice, but I just want to give you a caution, which is in this case, in any cases like it, use parentheses. So that you don't avoid not distributing incorrectly. So here's what I mean by butterfly. We're going to multiply those two and set them equal to those two. So it kind of looks like we're making a butterfly, right? So we get 8, and then this is what I mean by parentheses. So 8 times 3x plus 4, and then equals 11. And we need parentheses on that side also, times 7x minus 1. And as soon as we've done that, now we're just back to solving an equation like we've done 1,000 times at this point. So step 2 is just solve as usual. This is the, well, let me write this and then I'll tell you. So solve as usual depending on the type of equation. In this case, it's just a linear equation. So normal undo balance kind of steps. So to answer his question, is this the whole unit? The concept is the whole unit. So similarity and proportionality are roughly the same concept. With a figure, like let's say a triangle, we have to add the shape aspect to it, but like we can't have a triangle be similar to a rectangle. But even if they did have some similarity or proportionality amongst their side lengths. So it is the basis of the concepts. But the bigger deal is how do we set up what I just gave you? So if I give you two pictures, how do we get the equation set up in the first place? That's going to be a lot of our work. Okay, anyway, so we'll just put this in here as a review. I'm going to collect terms on the right side so the x stays positive. Let's see, 53x, so x equals 33 over 53. No, it's 53.
No, 33 is
Oh, sorry. $43, thank you. 43 over 53. So you can see that once you set it up, you're okay. The setup is going to be a lot of our focus. Any questions on how to solve these? Do you also see that we could set up in a way that would create a quadratic like our warm-up? In other words, if I just flipped this second fraction over, if I had given it to you differently, now we would have the 7x times 3x, and we would have 21x squared. Now we have a quadratic equation. Okay, that will come up for sure. All right, so moving on, let's have you solve a couple of these. Actually, maybe just one. Do I have any good ones? Yeah, we'll do those tomorrow. Let's do this one now. Go ahead and solve this one. I'll give you, I don't know, maybe 4 minutes. Maybe 5 minutes. We'll see how it goes. Okay, so there's our cross product set equal. Does it matter which side you put each one on, do you think? Like, is it okay if I had reversed negative 12 and all the parentheses stuff? Yeah, which in this case is more obvious. Well, the one we did in our example wouldn't have made a difference either. Okay, distribute, don't forget to hit all the terms, meaning like all things get multiplied. So we get x squared and then plus 3x minus 5x from the outer and the inner. Okay, now we need to combine our terms in order to solve. So we'll get x squared. In fact, let's just do it all together. Add 12 over there. So x squared minus 2x minus 3 equals 0. All right, what method should we use to solve that? That is a quadratic with a bx, so we'll try star. All right, do we have any factors of negative 3 that add up to positive, or negative 2 rather? What are they? 1 and negative 3. Okay. So our two factors will be x plus 1, x minus 3. Don't forget, we're still set equal to 0 here. Okay, and then we go in and separate, set each one equal to 0 individually. And we'll get x equals negative 1, x equals 3. In geometry, what would we need to do with those two?
Plug it in.
Yeah, plug both in and make sure that they don't make something like a length or an angle negative. Now, we won't be doing proportionality with angles because our angles will be congruent instead. So, questions on solving proportions. Are we good on that? Actually, let's do a fist to 5. Let's rate that. Just solving proportions. Okay, that looks awesome. So that was kind of a background to this first section. So have you heard the word dilation before in a math context? So dilation, scale factor, I've said several times today, and then similarity, of course. So it says solve for missing side lengths. Area and perimeter, pretty interesting. Well, area is with scale factor and similarity. So that'll be a day or two from now. And then, did you have a question?
What? No,
Okay. All right. So diving into similar now in a geometry context. It says Roosevelt High School sells a sticker and a larger car decal with the school logo. What does similar mean? I will tell you that the smaller and the larger stickers are similar. So if this is a geometry shape, what do you think similar means in that? Tobin, what'd you say? Okay. So definitely we can't be the same size. That's actually very important.
it's like the same shape, but maybe not the same. It's not good. It's the same shape.
Okay.
Same angle.
Same angles, like in terms of size, you mean? Yes? Okay. In terms of that, am I comparing this angle to that angle? So what's the word we used? Do you guys remember? Yeah, good. So we're going to have another CPCTC, but it's going to be CPSTP instead. Yeah. So corresponding is good. All right. What else? There's one more thing that we didn't talk about. Like in this trapezoid, we talked about the angles being congruent. Well, corresponding angles are congruent. But what else is making this trapezoid up? What else makes a trapezoid besides angles? Like, I'm not trying to trick you. Like side lengths, right? Side lengths. What do you think is true about them? They are? So if I compare those two sides, I'm not sure how to show it. Let's just say like that side to that side. Are they congruent? Okay. So what are they? Proportional. Yeah. Now, if I only have two side lengths, can I create a proportion? So, by the way, this member said it was a car decal versus a sticker. So let's say this is 5 inches and this is 2 inches. Do I have enough to write a proportion with just those measurements? No, because that's only two numbers. So I could do 5 to 2, That's a ratio, but I have no idea what goes over here. So we need a relationship between multiple side lengths to prove similarity. Does that make sense? Kind of why? So if we go maybe over here to this pair of side lengths, let's say I tell you that the bigger one, the decal, is 3 inches on that side. What would the bottom one have to be, the small sticker, to match? So if this is 3 inches, so you're sitting in the Mr. McCarty's design studio, like what do we need to make this bottom sticker? The smaller sticker. What do we need to make it? Can you solve that real quick? Now you kind of see why we reviewed the solving, because now we're talking realistic stuff. So the big sticker is 5 by 2, or the decal. What's that bottom length of the other sticker? Stick an X right there, set your cross products equal. You're going to get 5x equals 6. Right? So 6/5, which is 1.2 inches. Now we have a similar sticker to the decal. Okay? So yes, that is a critical part of this list. Side lengths are proportional.
Just use the more opposite side instead of
Well, so she's asking this. Could we have just used this and this side? What do you guys think? It's good to go in 2 dimensions, which I know, like if we get technical, this has an X and a Y coordinate, right? Because it's diagonal. But it's kind of the vertical nature of this decal, but this is the horizontal nature of it. So it would be good to have it in 2 different directions. Especially in this, what kind of trapezoid is this? Do you guys remember the name? Isosceles. And so both of the 2 non-parallel sides should be congruent. Normally, yes, I would say yes, you're right. We could have used that as well. Okay. So let's kind of think, what is that unit that we use to scale things down or up? Okay? And I'll talk to you about notation after that. So this black figure is our original. What are the dimensions of it? What are the dimensions of A, B, C, D? Melissa, how about you?
2, 3.
Yeah, so 2 by 3. Okay? Now, obviously, the orange one is a larger version. So what are the dimensions of it? 6 by 9. Okay? So corresponding sides tell us that we have to go this bottom side to bottom and this left side to left side. And the number that we multiply by to create that new figure is called the scale factor. In this case, what is it? Times 3. Okay? So in this case, the new figure, what we call the... Do you see these little tick marks up here? The dilated figure, it's got a scale factor of 3. So our dilation is by 3 times. Now, be careful how you think of that, but we'll just say it that way for now. The way we read these notes, these little tick marks, is we say prime. So A prime, B prime, C prime, D prime instead of just A, B, C, D. Okay? All right, let's try one of these. So what is the scale factor? That's what I'm asking. Don't shout this out. Just let me know when you can. or the factor of dilation, those kind of phrases. Usually we say scale factor. So raise your hand when you can tell me. Oh, that's a lot of you. Okay, go ahead. What'd you say? What'd you say? Okay. She says 2, 3, 3. Okay. So everybody's wrong, but Mike is the closest. Which one of these two is our original figure? Is it the black or the orange? Black. This is the original. Okay, so we're going big to small. And I said that the number we multiply by is the scale factor. So can I multiply the black one by 3 to get the orange one? Can I, and you said 2, which doesn't work at all, which is okay. It's hard to read these graphs sometimes. Micah said, tell everybody again what you said. He said divide by 3, which is an accurate process, but what is the scale factor? Okay, or 1/3, right? So to multiply, we would need to multiply by 1/3. Okay. So do you see how it's important to know which the original and which is the new figure is? Because if I said it the other way, if we went this way, what's the scale factor going that way? Now it's 3, okay? So it matters which is which here. So times 3 times 1/3. The direction, or what is the original versus the image is new. The new image is important. Okay, let's go put some of that stuff in our notes. These are concepts. If you need, I can write a little example in there as well. Okay, so this is, I'm writing this in red because it's pretty important. So the number we multiply by to get from the original to the dilated figure. Dilated means it's either bigger or smaller, by the way. I know when we, just in everyday life, when we say dilation, we're usually talking about bigger. Like, has anyone had their eyes dilated at an eye doctor? So they put drips in your eyes that make your pupil get really big. But it also means in math, smaller as well. So maybe we'll just make sure that's clear. Bigger or smaller. Okay, dilated, bigger or smaller. So basically what we just wrote can be summarized in this manner. Scale factor, SF, equals original, sorry, I wrote that wrong. New length over original length. As long as you're comparing, geez, I forgot all 2 words. Make sure to compare, what's that C word again? corresponding, I know I didn't give you much context for that. Corresponding sides. In other words, don't just willy-nilly. Low power mode. Uh-oh, I'm about to lose power. Don't just willy-nilly compare sides and divide or whatever to find your scale factor. Make sure you're comparing corresponding sides. So new length over original length will get you there. Everybody good? Got what you need? I know the first day of a unit, there's always a lot to talk about. Sorry. It's just the way it goes. Okay, let's try it on this one. It's not always going to be pictures. Actually, let's go here first. So again, if you read the directions, what is the scale factor? That's all. So scale factor. Raise your hand when you can tell me. Good. Got 2 hands up. 3, 4. 5. What was that face? Okay, everybody say, what's the scale factor? 1.5 or 3/2. Why? Which direction are we going? 12 to 18. It's 2/3 if we went the other way, right? If all the little tick marks, all the primes were on the black figure, then we'd go the other way. All right. How about this one? Raise your hand when you're ready. Okay. Go ahead and say 1/2, right? So the new length is 1 and the old length or original length was 2. So just 1/2. We could have done that up here too, actually. I should have. So new is 18 and the original or old is 12. So 1.5. Now, did you check both dimensions? Is it that way here as well? Yeah. So 4/2, right? Sorry, I wrote it wrong. 2/4. So are those figures similar, do you think? Same scale factor. We can't measure the angles, but if we were told they're the same, then we would be fine. Just to point out the language that some geometry texts use, image and pre-image. What do you think? Like, let's look at the rectangles here, image and pre-image. Which one is the black one? Is it the image or the pre-image? That's the pre-image. And then this is the image. I think that vocabulary is good to know. It's a little confusing sometimes. So that's why I kind of tell you like original versus new. All right, what do you think of these 2 questions? Are Fords similar to Chevys? We're going to define this, and then probably you'll have a few minutes to try some of these problems. This isn't too bad. It kind of goes back to like how deep do you want to go with this, right?
What's it say?